everyone, I'm Mary Joy Emianwaria from BSCS 4B. So I'm here to discuss about Completely Fair Scheduler. So what is Completely Fair Scheduler? The Completely Fair Scheduler is a process scheduler that was merged into the 2.6.23 release of the Linux kernel and is the default scheduler of the task of the Sched normal class. Next is overview of CFS. The main idea behind the CFS is to maintain balance or fairness in providing processor time to task. This means process should be given a fair amount of the processor when the time for task is out of balance, meaning that one or more tasks are not given a fair amount of time relative to others. Then, those out of balance tasks should be given time to execute. To determine the balance, the CFS maintains the amount of time provided to a given task in what's called the virtual runtime. The smaller a task, virtual runtime, meaning the smaller amount of time a task has been permitted access to the processor, the higher its need for the processor. The CFS also includes the concepts of sleeper fairness to ensure that tasks that are not currently runnable, for example, waiting for I/O or the input or output, receive a comparable share of the processor when they eventually need it. Then next is Figure 1, example of a red-black tree, with tasks represented by Sched entity objects stored in the time-ordered red-black tree. Tasks with the gravest need for the processor or lowest virtual runtime are stored toward the left side of the tree. And the task with the scheduler then, to be fair, picks the leftmost node of the red-black tree to schedule next to maintain fairness. The task accounts for its time with the CPU by adding its execution time to the virtual runtime and is then inserted back into the tree if runnable. In this way, tasks on the left side of the tree are given time to execute, and the contents of the tree migrate from the right to the left to maintain fairness. Therefore, each runnable task chases to the other to maintain a balance of execution across the set of runnable tasks. Next is CFS internals. All tasks within Linux are represented by a task structure called task struct. This structure, along with other associated with it, fully describes the task and includes the task's current state, its stack process flags, priority, or both static and dynamic, and much more. You can find this and many of the related structures in that Linux include Linux Sched.h. But because not all tasks are runnable, you won't find any CFS related fields in task struct. Instead, a new structure called struct entity was created to track scheduling information. See in the figure 2. So this is the figure 2, structure hierarchy for tasks and the red-black tree. The relationships of the various structures are shown in figure 2. The root of the tree is referenced via the RB root element from the CFS RQ structure or in that kernel Sched.c. Leaves in a red-black tree contain no information, but internal nodes represent one or more tasks that are runnable. Each node in the red-black tree is represented by an RB node which contains nothing more than the child references, and the color of the parent. CFS features. CFS supports symmetrical multiprocessing, or the SMP, in which any process, whether kernel or user, can execute on any processor, yet configurable scheduling domains can be used to group processors for load balancing or event segregation. If several processors share the same scheduling policy, then load balancing among them is an option. If a particular processor has a scheduling policy different from the others, then this processor would be segregated from the others with respect to scheduling. Next is CFS implementation. CFS requires efficient data structures to track task information and high-performance code to generate the schedules. Let's begin with a central term in scheduling, the run queue. This is a data structure that represents a timeline for scheduled tasks. Despite the name, the run queue need not be implemented in the traditional way. As a FIFO list, CFS breaks with tradition by using a time-ordered red-black tree as a run queue. Next is priorities and CFS. CFS does not use prioritize directly, but instead uses them as a decay factor for the time a task is permitted to execute. Lower priority tasks have higher factors of decay, where higher priority tasks have lower factors of delay. This means that the time a task is permitted to execute dissipates more quickly for a lower priority task than for a higher priority task. That's an elegant solution to avoid maintaining run queues per priority. Next is scheduling classes and domains. Also introduced with CFS is the idea of scheduling classes, or recall from Figure 2. Each task belongs to a scheduling class which determines how a task will be scheduled. A scheduling class defines a common set of functions, or via sched class, that define the behavior of the scheduler. For example, each scheduler provides a way to add a task to be scheduled, pull the next task to be run, yield to the scheduler, and so on. Each scheduler class is linked with one another in a singly linked list, allowing the classes to be iterated, for example, for the purposes of enablement of disablement on a given processor. So next is Figure 3, graphical view of scheduling classes. But recall that the scheduling classes are part of the task structure itself. See in the Figure 2. This simplifies operations on tasks regardless of their scheduling class. For example, the following function preempts the currently running task with a new task, where car defines the currently running task, or RQ represent the red-black tree for CFS, and P is the next task to schedule from that kernel sched.c. And lastly, going further, if there's one constant with Linux, it's that change is inevitable. Today, the CFS is the 2.6 Linux scheduler, but tomorrow it could be another new scheduler, or a suite of schedulers that can be statically or dynamically invoked. There's also a certain amount of mystery in the process behind the CFS, RSDL, and kernel inclusion. But thanks to both Kolivas and Mornell's work, we have a new level of fairness in 2.6 task scheduling.